Oh, this is too depressing. I don't know any history. You guys know history? 30 Years' War, really bad scene. Like, I didn't realize quite how bad until I read it on Wikipedia. Like,
which one is this?
30 Years' War? I want to say like mid.
Russia and Napoleon.
No, it's earlier than that. Oh, Jesus. Where's the, there we go.
I think it's like 1600 sometime.
30 years. I'm not going to ask Cleverbot anything ever again in my entire life. So, early 17th century. Longest continuous war in modern history, if you call that modern. So anyway, it was really, really bad, like very totally gruesome. In some regions of Germany, 3/4 of the population died. The male population of Europe reduced by almost half. German population reduced by 30%. Like, this is not good. So I just point this out because that's the environment where Leibniz was born. He was born at the end of the 30 Years' War, and he's the guy that along with, he came up with the idea that Frege fulfilled in inventing first-order logic. Leibniz's dream, a general method in which all truths of the reason would be reduced to a kind of calculation. Oh, also inventor of calculus, right? Except calculus just means like a formal system of reasoning. So he called it the calculus of infinitesimals. The calculus of infinitesimals. So, but he also had this other kind of calculation, this universal language or script, but infinitely different from all those projected hitherto, for the symbols and even the words in it would direct reason. The symbols are directing reason. And errors, except those of fact, would be mere mistakes in calculation. If controversies were to arise, we wouldn't go to war and kill half the population. There would be no more need of disputation between two philosophers than between two accountants, for it would suffice to take their pencils in their hands and say to each other, "Let us calculate." So this is sort of one of the foundational touchstones of AI, that we know stuff, so there must be a way to represent things that we know, and we seem to make inferences, and maybe there's a way of mechanizing that, of formulating it in an algorithm. So it's very old roots. So I'm a big fan of Leibniz. Yeah, okay, so this is everything else you need to know about logic. We talked about natural deduction, we talked about modes of inference. I haven't talked about Horn theories yet. So this is something, just one of those random things you have to know. They're named for this guy, Horn. Sorry?
Why would they name it after the guy who invented it?
Yeah, it's silly the way that happens. I guess he was a nice guy, I don't know. Horn, something is horn if it looks like that. So you can have first-order horn. This is propositional horn. You've got an and of some stuff implies something. All right, that means it's horn. If it walks like a duck and it talks like a duck, it's a duck. Very common sense. Horn clauses are just very commonsensical. Now, if you talk to someone, they'll tell you that a horn, they won't give you this as the definition of a horn clause. Who was having trouble with this the other day? I want to pick on them. What's implication, if we want to rewrite implication? Not, yeah, so if you have A implies B, we want to write not A or B. So if we have, where's my desktops have gotten all messed up. What happened to, is now I'm supposed to go like, there we go. Whoa, I've got, are they out of order now? I'm so confused. A full screen isn't a desktop. Okay, I'm so glad we're using a Mac. Okay, so we had if it's X and it's Y, then it's Z. If X and Y, then Z. So if I want to rewrite that, if A implies B is the same thing as not A or B, then this is not X and Y, or Z. Not A and B means, as we all know, not this or not that, or Z. Everyone cool with this? So the technical definition of a Horn clause is a clause with at most one positive literal. At most. Yep. You could have just...
Not X, not Y, or not XC.
Yeah, you could have that. Yeah. Yeah. At most one positive literal. So these are negative, and that's positive. So that's Horn. At most one positive. They're also called positive definite clauses. Okay, now I'm totally confused. Now, if this is a full screen and I make it go away, now does it become a desktop? Anyway, where are my slides? Here we go. Okay, so that was one positive literal. Exactly one positive literal is a definite clause. So this you can think of this as a definition of being Z. Like in order to be Z, you've got to be these other things. So people find these incredibly natural to write down. And there's, in fact, an entire programming language called Prolog, where you write programs in using definite clauses. These are very definitional. So this is, in Prolog, that's an implication going that way. So if it's furry and meows, it's a cat. If it's a feline, it's a cat.
You said that in order to be Z, you must be those things. That is not the case.
Well, because that's propositional, but in first order, like if X of thing and Y of thing, then Z of thing. Yeah, okay, fine.
You walk like a duck, you talk like a duck, you're a duck.
Yeah.
A duck does not necessarily walk like a duck or talk like a duck.
Yeah, so there might be many ways of being Z, and this is one of them. Just like for a word might have many meanings. Yeah, okay, I didn't mean to imply that this was double implication or something. Yeah. So in Prolog, you write out definite clauses, and then you give some facts. These are definite clauses. They have exactly one positive literal, no negative ones. And then you say, hey, is there anything that's a cat? And your Prolog system will come back and say, A. If you have a bug in your Prolog program, it might come back and say no. So everyone loves to joke about writing this big Prolog program, and then they type in their query, and the computer just says no. Yeah, I think so. Yeah. That makes sense, right? Yeah. Horn, why am I making a big deal about Horn theories? Because for propositional logic, Horn reasoning is easy. Linear time. Modus ponens is sound and complete and linear time for Horn KBs, which is fabulous. Like, oh my God, wow. So a lot of people wondered, gosh, like how much of human reasoning is Horn? Now, just to do a very sketchy little proof of this, you can think of each of these as being a rule. Like, if something is this and this, then it is this. So it's like an if-then, like a rule. And for all the ground facts, they're going to cause a rule to fire. So Prolog has unification built in, and it will unify the A with the X and substitute it in here, so you get cat of A. Each rule fires at most once. So the amount of time it's going to take is going to be linear in the number of rules. People often even use a term called a rule-based system or an expert system for systems that for Prolog programs that are written like this. And in the 80s, there was a huge industry in AI expert systems. And you'll still hear about them today. And it's just a very simple, it's a simple form of reasoning that is efficient. Now in first order, it's actually like Prolog is actually first order, so it's actually not efficient. Prolog actually takes some shortcuts. Prolog does not perfectly adhere to first order logic. But I'm not going to talk about that. But you hear about knowledge-based systems or expert systems or rule-based systems, and that's basically what they are, is reasoning with definite clauses. So if you understand first-order logic, you understand all these special cases really quickly and easily. So Horn clauses, important to know about. So someone asked at the beginning of class about can we approximate first-order logic? And so people have done work where you like make your knowledge base Horn by throwing out stuff. So you have a different KB than what you had before, but now it's Horn, and a lot of reasoning is faster. And it's approximate, but you can sometimes prove various guarantees, like that if you can prove that something's true, then it's definitely true in the full theory. Stuff like that. This is another special kind of logic that people have come up with. And people like it because they're pictures. You can draw little diagrams of, like, oh, there's Mary. She's not just some symbol. Like, there she is. And she's a member of the class of female persons, which is a subclass of persons, which is a subclass of mammals. And you can make these big taxonomies. So psych, for example, a lot of psych looks like this. It's a taxonomy of classes and instances. UML is like, very much like this. And this is all just a graphical representation of a certain kind of first-order knowledge. But it's extremely limited. So each of these links represents a predicate. So here we have, sister of Mary John, for example. Yeah. So this is one thing that people do in these are called semantic networks or conceptual graphs or frame systems. One thing that people do that's a little nasty is stuff like this, and first-order logic cannot do this. And so there's been a lot of work in trying to figure out, well, does that mean that semantic networks have no semantics? Or like, what if we want to actually come up with how this should work? There's a lot of work on this. Here we've said that people have two legs, but John is special and has only one. Liz Long John Silver, I guess, from Treasure Island. So there's an inheritance hierarchy here where Mary, nothing's been said about the number of legs she has, so she inherits the leg property from the person's class by default. Whereas here, John, we've said something very specific about the number of legs he has. So when we look up the number of legs he has, we stop here. So this is what's called non-monotonic. In traditional deductive logic, if you keep adding things to your KB, you can make more and more resolutions and prove more and more things true. But anything you've proved doesn't become false when you add new stuff to the KB, unless you've made your KB inconsistent. Here, we've added something, and we previously would have inferred that John had two legs, and now we add this, and now we infer he has only one. So that's a non-monotonicity. So how to deal with defaults in logic is a very tricky issue, and I don't know that much about it, except that there's a lot of work on it. It was one of John McCarthy's big things in the last 20 years of his life, how to deal with defaults in first-order logic. And there are lots of ways of doing it. But anyway, semantic nets started it off just by doing it in a completely ad hoc way, where you just look up the hierarchy and there you go, and to hell with how it relates to actually any real logical system with any semantics. So this is a semantic network. But you can view them as through the lens of first-order logic, as just a special way. Now, there are a lot of things semantic nets can't do. For example, what's one thing you can't represent with something like this? You instantiate instances and link them up here. Can anyone see something we can do in first-order logic? Why, God, there's a whole list of all the exciting things we can do in first-order logic that I got all excited about, and a lot of them we can't do here. Does anyone remember what any of those things are?
Everybody loves somebody?
Yeah, universal quantification. Well, I think you could do that by saying for all, I guess we've said here that all people have a mother who is a female person. So this is kind of like a universal quantification. But keep going with that thought. Like, what else could we do in first order logic that?
Mary likes one of John's ties.
Yeah. So existential quantification. Like, there exists something, but we don't quite know what it is. Here, you can only talk about actual instances. So, that's really annoying. You don't have disjunction. Like, it's either this or it's a that, but not both. Can't do that. In fact, you can't even represent negation here. John does not have one leg. Can't say that. Sorry. Your hands are tied. It's a very limited kind of logic. As a result, it's extremely fast. There are all these things you can't say, so it's pretty darn quick. If you want to look up a property of someone, it was something true of someone, it's log time up, you just go up the hierarchy. And so people have formalized semantic networks, and the term people use nowadays is description logic. And that's kind of, there's something called OWL, the web ontology language, that people have put a lot of work into, which talks a lot about classes and taxonomies and what class inherits or subsumes from what other class. And description logics don't have negation or disjunction or nested functions or existentials or intractability, which is great. So, like, these are all bad things, but then this is really nice that they're missing the intractability of first-order logic. So, anyway, a lot of folks in business care about description logics. So now at least you know what they are.